All right, in this video, we're going to talk about section 3.4 dealing with multiplication of whole numbers. And in this video, we'll solve multiplication problems using various models. We'll use properties of multiplication to develop computational strategies. We'll use multiplication algorithms, including the standard algorithm, to solve problems. And we'll use mental multiplication skills and estimation techniques. All right, let's start with multiplication of whole numbers. Now here, we can model multiplication of whole numbers in several different ways, like the repeated addition model. Sometimes multiplication is referred to as repeated addition because we're repeatedly adding the multiplicand multiplier times. Okay. So in this case, if we have 4 groups of 3 brushes, we can use addition to put the groups together. When we put equal size groups together, we can use multiplication. We can think of this as combining 4 sets of 3 objects in a single set. All right, so here's the case right here. If we add the 3 4 times, here you got 4 3s added together, you'll get 12. And we can use colored blocks to represent, in this case, 5 times 4. So you got 4 purple blocks, well, actually 5 blocks of 4s. Or on a number line, we can just go to the right 4 5 times. You'll end up at 20. Okay. And by the way, the word multiplicand and multiplier is this. The first number will be the multiplicand. And the number we're multiplying the 5 by, which is a 4, that is your multiplier. Okay, that means 5 is being multiplied. That means 5 is being added 4 times. That's basically what that means when we deal with multiplier and multiplicand. All right, now the definition of multiplication of whole numbers using the repeated addition model. For any whole numbers A and natural number n times A means this. We're adding A n number of times. Okay, so we have n terms of A being added. Right. Now, the other model is the array and area model. Multiplication can be visualized by constructing an array of crossed sticks or grid and counting intersection points or grid components, respectively. Like if I wanted to do 4 times 5 is equal to 20, I can have like 4 sticks going across, and then 5 sticks going straight up and down. Here I got 20 intersecting points. So if you count up the number of intersecting points, you'll see that there are 20. So 4 times 5 will be 20. And also a grid that looks like this. 4 rows of 5. Or in this case, 5 columns of 4 blocks. So 4 times 5 will be 20. All right, another model would be the Cartesian product model. Now, back in chapter 2, we did talk about the Cartesian product with 2 sets. And we can create those as a set with ordered pairs. Here, the Cartesian model is applied in multiplication, and that can be thought of in terms of Cartesian products. Let's say we want to take 2 web-based courses at your local college. You can take one of the following: World History, Ancient History. And then for your second course, you can take one of the following: Latin, French, or German. To show the number of different schedules you could have, you can use a tree diagram. And the way of designing your schedule are a result of selecting a history course from the set of H, which is world history, and ancient ancient history, and a foreign language, which will be set L, consisting of Latin, French, or German. And then you design the Cartesian product using a tree. So it'd be H times L. So here you have world history, and then your ancient history, which is your history, and then a language, a foreign language. You can take world history, you can take either Latin, German, or French. Or if you take ancient history, you can take Latin, German, and French. So these are all the possibilities. And in this case, you'll see that there are 6 possible schedules based on what's given for H and for L. So let's take a look at this homework example. If A has the elements C and F, and B has the elements G, M, and T, we can complete the following by finding A cross B. And keep in mind, these are sets. So that means it's just the cross product of A and B. So here's part A. A has the elements C and F, and B has the elements G, M, and T. And if I want the cross product, if you recall, we take each element of the first set, pair it with each and every element of the second set. So C will be paired with G. C will be paired with M. C will be paired with T. And then we pair the F with each and every element in B. So F will be paired with G. And then F will be paired with M. And F will be paired with T. Okay. That's how we find the cross product of A and B. Now in part B, we want the number of elements in that cross product of A and B. Well, we just count up how many ordered pairs we have in this set for A cross B. And in this case, there's 6. And then part C is to write a multiplication equation involving numerals related to the answers in parts A and B. Well, in this case here, in set A, there are 2 elements times the number of elements in B, there are 3. We ended up getting 6 ordered pairs, as you can see. So a multiplication equation for that would be 2 times 3 equals to 6. Okay. Now here's the definition of multiplication of whole numbers using the Cartesian product. For finite sets A and B, if the number of elements in A is equal to little a, and the number of elements in set B is equal to small b, then A times B represents the number of elements in the cross product of A and B, which I just illustrated in that first homework example. Okay. Now in homework example number 2, it would be best to use what they call the fundamental counting principle or the fundamental multiplication principle. Like in this case, a designer has designed different tops, pants, and jackets to create outfits. How many different outfits can the models wear if she has designed the following pieces? And that is 8 tops, 4 pants, 6 jackets. This is where I use that fundamental multiplication principle by just multiplying the 8 times 4 times 6. Well, here 8 times 4 would be 32. And then 32 times 6 would be 192. So in this case here, there are 192 different outfits that the models can wear if the designer has designed the following pieces. Okay. Now, in this alternate definition, sets A and B do not have to be disjoint. The expression A times B, or simply AB, is the product of A and B. And the numbers that we're multiplying, the A and the B, they're considered to be factors. Okay. So when we multiply something and we get an answer, that answer is considered to be the product of your factors. Okay. So now let's look at another homework example. In each of the following, find if possible a whole number that makes the equation true. And sometimes you have to think about these type of problems here, like in part A, 3 times some z is equal to 12. And we want to know 3 times what number would give us 12. And in this case, that z will have to be 4, because 3 times 4 does equal to 12. All right, now in part B, we got 36 is equal to 18 plus 3 times z. Now, you can think of this as an algebraic equation and try to solve for z, but it will be best to try to do guess and check, which is one of the strategies for problem solving. Try to think of 3 times what number, and then add 18 to it. That will give you 36. Well, if I try 6, it'll be 3 times 6, that would be 18. 18 plus this 18 will be 36. So that number there would be 6. And now part C, we got z times 4 plus 6 is equal to z times 4 plus z times 6. In this case, I can try any number for z. And what's going to happen here is that the left side will be equal to the right side. Example of that, if I try 3, I know 4 plus 6, that's 10. 10 times the 3 would give us 30. And on this side, 3 times 4 is 12. 3 times 6 is 18. 18 plus 12 will also give me 30. Now I can try any number for z. Here, the left side will always equal to the right side. So we can think of this as any number will make the equation true. Any number will make the equation true. Okay. All right, on the next page is properties of whole number multiplication. Okay, so we're going to be revisiting these properties that we talked about back in section 3.2 when we were dealing with addition of whole numbers. Now for whole number multiplication, we do have these properties. One of them is the closure property of multiplication of whole numbers. And that is, if A and B are whole numbers, then the product of A and B will be a unique whole number. Let's say 8 times 7. I'm going to get a unique whole number for 8 times 7, which is 56. And then we got the commutative property of multiplication of whole numbers, where if I have A and B being whole numbers, then A times B will be equal to B times A. And again, I did talk about commutative back in section 3.2. And commutative property means that the order does not change. So the order of the two numbers that I multiply will not change. like 3 times 5, that's 15. I can switch the 3 and the 5 around and say 5 times 3, that will still give me 15. Okay, and here is concrete evidence of that. 3 rows of 5 or 5 rows of 3. Now let's look at a homework example. Here we want to determine whether the following sets are closed under multiplication. Starting with, and let's think about this. When it's closed, that means that the product of the two numbers has to be in each of those sets in order for it to be closed under multiplication. Let's take 0, 6. Now, if I multiply 6 times 6, that's going to give me 36. Is 36 in this set, 0, 6? The answer there will be no. So this is not closed under multiplication. Now, part B, 3, 6, and 9 with the 3 dots. That's the ellipsis. That means that this set is an infinite set. It continues on and on. Well, if I do 6 times 9, that's 54. And 54 is a multiple of 3. So that means that 54 has to be included in this set. So this is closed under multiplication. And this one, 3, 5, 7, 9, and so on. I want to determine if that's closed under multiplication. And in this case, if I take, let's say 5 times 7 is 35. And that set represents odd numbers that are greater than 1. And 35 is an odd number, so that means it must be closed. It is in that set, so it must be closed under multiplication. All right, now let's look at some more properties like the associative property of multiplication. That's where the grouping does not change the answer. In other words, if A, B, and C are whole numbers, then if I first multiply the A times B first and then multiply that product by C, I get the same thing as if I multiplied B times C first and then took that product and multiply it by A. And here's an illustration of that. Here we got 3 times 5 times 4. So here I got 3 stacks of 5 by 4 blocks, or 5 times 4. And here I have 4 blocks of 3 times 5. They're both the same. Because if I multiply 5 times 4 first, I would get 20. 20 times 3 will be 60. Or do 3 times 5, that would be 15. 15 times 4 is also 60. Okay, so in this case here, with the associative property, the grouping of two numbers does not change the answer. And here's some more properties here on the next page. One of them is the identity property of multiplication of whole numbers, meaning that there is a unique whole number 1, such that for any whole number A times 1 would give us A, or 1 times the number A would also give us A as well. So any whole number multiplied by 1 will give you that whole number back. Also, there's a multiplication property of 0 for whole numbers. So any whole number A multiplied by 0 would give you 0. Or 0 multiplied by any whole number A would still give you 0. And then we got the distributive property of multiplication over addition for whole numbers. So if I have any whole numbers A, B, and C, then that means A times the quantity B plus C in parentheses. That's how we appropriately read that. that's going to be equal to A times B plus A times C. In other words, if I have a number on the outside times something on the inside, I can take that and distribute it over what's on the inside through multiplication. A times B plus A times C. And this also applies to subtraction of whole numbers as well. So again, A times B, which is this, and now it's going to be minus A times C. And that's for any whole numbers A, B, and C. Now, because the commutative property of multiplication of whole numbers holds, the distributive property of multiplication over addition can be rewritten like this. The quantity B plus C multiplied by A. In other words, I can do this. B times the A would be B times A, and then plus C times A, that'd be CA. And also the distributive property can be generalized to any finite number of terms. So if I have A times the quantity B plus C plus D, the A can be distributed over the B and over the C and over the D by multiplication. So it'd be A times B or AB plus A times C, which is AC, plus A times D, which is AD. All right, now, in this homework example here, which property is illustrated in each of the following? Starting with part A, you got 8 times, and in parentheses, 4 plus 6, and that's equal to, and in parentheses, 8 times 4 plus 6. Now, if you notice the difference between the left and the right side, you'll see that the order of the numbers are still the same. The only thing different is the grouping. We group the 4 times 6 on the left side, but on the right side, we group 8 times 4. So that is considered to be the associative property of multiplication. Associative property of multiplication. All right, now part B. We got 8 times, and in parentheses, 4 plus 6. And then on the right side, equal to 8 times. And notice we got 6 times 4 in parentheses. Now, let's be careful here. Let's look at this very carefully here. The 4 times 6, and then on the right side, you got 6 times 4. Notice that the order has changed. We changed the order of these two. So that is considered to be the commutative property of multiplication. Commutative property of multiplication. Okay. Now part C, we got 8 times, and in parentheses, 4 times 6. And then on the right side, we got 4 times 6 in the parentheses times 8. Notice the order has changed. The 8 is in front here, but on the right side, the 8 is behind. The order has changed. So again, this is also the commutative property of multiplication. Okay. Now part D, we got 1 times, and in parentheses, 4 times 6. That's equal to 4 times 6. So here, 1 times this gave us this back. So we call that the identity property because we're using the unique whole number 1. So this is the identity property of multiplication. Now part E, 7 plus 1 in parentheses, and then that's multiplied by 0, that will equal to 0. Okay, well, anything multiplied by 0 is 0. So that means we have the multiplication property of 0. Or sometimes called the 0 multiplication property. They're both the same. And part F, 8 plus 4 in parentheses times the 7 plus 6 in parentheses. That's equal to 8 plus 4 times the 7 plus 8 plus 4 times the 6. Notice, in this case, they're distributing the 7, they're distributing the 8 plus 4 over the 7, and 8 plus 4 is being distributed over the 6 through multiplication. So we call this the distributive property of multiplication over addition. So that's how we identify these particular properties here. All right, on the next page, when the distributive property is written as AB plus AC equaling to A times, and in parentheses, B plus C, we call that factoring. Okay. So in factoring, we're always trying to find a common factor that's in both of the terms and then divide. Okay. So this is just the opposite, going in the opposite direction. So here the factors of AB plus AC are going to be the A and the B plus C. So like in this homework example, number 6, let's say we want to use the distributive property of multiplication over addition. We can factor as in x squared plus xy equaling to x times the quantity x plus y, because notice that in x squared and y, the common factor is x. Then x times what would give us x squared plus y? Well, if you do x squared divided by x, you'll get x. And then xy divided by x will be plus y. Now we're going to use that distributive property of the distributive property and other multiplication properties to factor each of the following expressions, starting with part A, xy plus y squared. Let's find the common factor that's in both the xy and the y squared. It's got to be y. And we use the common factor with the smallest exponent. And it's going to be y to the 1. Now to get what's inside the parentheses, we divide each of these terms by x. So let's think of this. Xy divided by x is x. I mean, this should be y down at the bottom, not the x. Because the common factor there is y, as you can see. So xy divided by y, you'll be left with x. And then plus y squared divided by y, you'll be left with only a y. Because I can break y squared up as y times y. So it'll be y times the quantity x plus y. And you can check by distributing the y over the x plus y. If you do y times x, you'll get xy. And then if you do y times y, you'll get plus y squared. Part B, xy plus x. So here we need a common factor that's in x, y, and in x. And as you can see, the x is the common factor, so the x will be on the outside. So now to get what's on the inside, you'll divide each and every term by x. So here, xy divided by x, the x's will be gone, you'll be left with the y, plus x divided by x divided by itself will be just plain 1. So it'll be x times the quantity y plus 1. And then distribute to get this back as a check. X times y will be xy, and then x times a plus 1 will be plus x. All right, and then part C, a squared b plus ab squared. And here I want to factor this using the distributive property. All right, in this case, we need the common factor that's in a squared b and ab squared. Well, a is in both of these, but we have to use the one with the smallest exponent. So it'll be a to the first power. The same thing with b is in both of these, so we need to use the one with the smallest exponent. So it'll be b to the first power, or just b. So a times b is the common factor. And then we're going to divide each of these by that common factor of ab. So if I have a squared b divided by b, the b's will divide out. A squared divided by a would just be a. Plus ab squared divided by a. The a's will divide out. B squared divided by b will be b. And we can verify that by just doing the distributive property. You should get this back. AB times A will be A squared B, plus AB times B will be AB squared. All right, next we'll use an area model to show that x plus y times z plus w is equal to xz plus xw plus yz plus yw. All right, so if I use an area model, that means I can just draw a rectangle. I'm going to need 4 boxes here. X plus y, I will put x here and then y here. Z plus w will be z here and w here. And then I just multiply here. X times z will be xz. X times the w will be xw. Y times z will be yz. And then y times w will be yw. Okay, and I have nothing to combine with any of these terms here. So this ends up being this, xz plus xw plus yz plus yw. That's what that is, using the area model. And then we can also use a distributive property over addition to show that x plus y plus z plus w will equal to xz plus xw plus yz plus yw. Okay. Okay. So what I'm going to do here is distribute the x plus y over the z and over the w through multiplication. So this right here, if I distribute that x plus y times z, it'd be this, and then plus distribute the x plus y with the w, it'd be x plus y times w. And then again, I distribute the z over the x plus y and distribute the w over the x plus y through multiplication. So here, the z times the x, that'll be xz. Then the z times the y will be plus yz. And then plus w times x would be xw, plus w times y would be yw. And if I want this to look like this, I can use the commutative property, bring this down and change the order here of the yz and the xw. So it'll be plus xw and then plus yz plus yw. So here I'm using the distributive property of multiplication over addition to verify this. Okay. All right, on the next page deals with properties of exponents. Now we kind of talked about what exponents are, or a to the n. So here, if a, which is your base, and n is the exponent, are whole numbers with n not equaling to 0, then a to the n breaks up as this, a times, and so on. So a would be multiplied n times. That exponent tells us how many times a will be multiplied, will be used as a factor. And also a to the first power is understood to be a. Okay. Now here's some other rules for exponents. The product rule for exponents states this: for any whole number a and natural numbers m and n, then a times n, a times m times a times n will be equal to a to the m plus n. If I multiply powers of the same base, I bring over the base and then add the exponents. Example of that would be something like this: 4 to the 7 times 4 to the 8. Here the bases are the same, and I'm multiplying powers of the same base. So I bring over that base, add 7 and 8 together, you'll get 15. So, and this should be 7, 4. So it'll be 4 to the 15th, or 4 to the 7 times 4 to the 8. And then next is raising a power to a power. Let's say a to the m raised to the n would be a to the m times n. So anytime you're raising a power to a power, you bring over the base, multiply your exponents. So for something like 5 to the 3 or 5 cubed raised to the 6, we bring over the base of 5 and multiply 3 times 6, which is 18. So it'd be 5 to the 18th power. And then this rule says, if I have, let's say, a to the n times b to the n, notice here, your exponents are the same. So I can write that as the base times the other base raised to the n power. Let's say I had x to the 5th, y to the 5th. And I'm multiplying those two. Notice that the exponents are the same. So I can write this as x times y raised to the 5th. That's just the inverse of raising a product of a power to a power. Well, a product to a power. X and y multiply together and it's raised to the 5th would give me this back. X will be to the 5th and y will be to the 5th. And then the next theorem is this: a, m, and n are natural numbers, and here your m is going to be greater than n. Then this is what's going to happen. Here we're dividing powers of the same base. We bring over the base and then subtract the exponents. This is actually the quotient rule for exponents. So if I had something like this, 8 to the 9th, and I want to divide that by 8 to the 4th. If this exponent, this first exponent is bigger than the second exponent, okay? And I'm dividing powers of the same base. So I bring over the base and then subtract the exponents. So it'd be 8 to the 5th. That's the final answer. So these are just properties of exponents. They're going to be coming back up as we move along in this particular course. Here's an example. Let's say we want to write the following with only one exponent. So in this case here, we got 2 to the 6th times 8 to the 5th times 16 to the 3rd power. Okay, so let's say I want the base to be the same. I know this. 8 can be written as this, 2 times 2 times 2, which can be shortened as 2 to the 3rd. And 16 is going to be 2 times 2 times 2 times 2, or 2 to the 4th. Because I know 8 is a multiple of 2 and 16 is also a multiple of 2. And I've already got 2 to the 6th. So here I'm going to have 2 to the 6th times, and I'm going to replace that 8 with what is equal to, with a base of 2, 2 to the 3rd. And that's going to be raised to the 5th. 16 is 2 to the 4th. So that's going to be 2 to the 4th, and that's raised to the 3rd power. And here I'm going to use the power rule for exponents on these two right here. So let me bring down 2 to the 6th. And here I'm raising a power to a power so I can multiply those exponents. So I bring the base of 2 down, multiply 3 times 5, that's 15, times, bring the 2 down here, I'm raising a power to a power again, multiply your exponent. So 4 times 3 would be 12. And now I'm multiplying powers of the same base. So the base is 2, I'll bring that down and then add these exponents, add 6 and 15 and 12. This will be 2 to the 33rd power. 2 to the 33rd power. So here I'm writing this, I've given my final answer with only one exponent and one base. All right, next we'll look at some multiplication algorithms. Here we can use base 10 blocks to develop the standard multiplication algorithm. Let's consider 13 times 3. Using base 10 blocks, 13 can be written as 1 flat and 3 longs. And it's going to be times 3, so I can write 3 sets or put down 3 sets of 1 flat and 1 long and 3 unit pieces. 1 long, 3 unit pieces, 3 times. And if you were to simplify this, this is 10, 20, 30, plus a 9 would be 39. Okay. And here's another way of showing 13 times 3. 1 10 and 3 ones times 3 ones. Because that's a representation of 10 plus 3, and then times 3. Well, 3 times 3 will be 9, and 3 times 10 will be 30, which will give you 39. And the 9 and the 30, as you can see here, are what we call partial products. Add those together, you'll get the 39. Another strategy would be multiplying by 10 to the n. To multiply by 10, you replace each piece with a base 10 piece that represents the next higher power of 10. replace each unit with a long, and replace each long with a flat. So like, in this case, 23 times 10. 23 can be represented with 2 longs and 3 units. And we're multiplying by 10. So for each long, we're going to replace it with a flat. So this long will be replaced with a flat, and this long will be replaced with a flat. So we have 2 flats. And for each of these unit pieces, we're multiplying by 10. So each of these unit pieces will be replaced with a long. So those 3 unit pieces will be 3 longs, since we're multiplying by 10. And this is what our answer is going to be. 2 flats, 3 longs, which represents 230. And then we have multiplication using expanded addition, like 4 times 367. Well, we're going to expand 367. So we bring over the 4, expand 367 as 3, which is in the hundreds place, that's 3 times 10 to the second. The 6 is in the tens place, that's 6 times 10, and then plus 7. Now we distribute the 4 over what's in the parentheses through multiplication. So you're going to have 4 times 3 times 10 squared plus 4 times 6 times 10 plus 4 times 7. Now they use the associative property here to, group the 4 times 3 and then group the 4 times 6. Well, 4 times 3 is 12 times 10 squared will be 1200. 4 times 6 is 24 times 10 will be 240. And then, of course, 4 times 7 is 28. Add those partial products together, you'll get 1468 for 4 times 367. And they've also shown this vertically as well. 7 times 4, that's 28. 6, which is in the tens place, that's 60 times 4, that's 240. And the 3 is in the hundreds place, that's 300 times 4, which is 1200. Add those partial products together, you'll get 1468. Now here's some algorithms for partial products. The partial products algorithm for multiplication starts with thinking of the place value of each digit, then thinking of the numbers in expanded notation and computing all partial products, working one place value at a time. Finally, all the partial products are added together. So let's consider 14 times 23. And this is illustrated on the next page. Okay. So 14 would be like 1 flat. Well, actually, here's 10 and 4, that's 14. And here's 20 and 3 represented by 23. Notice that 10 times 20, that's 200. That's going to be 2 flats. And then 10 times 3, which is 30, that will be 3 longs. And then here, 4 times 20, that will be 80. That will be 8 longs. And then 4 times 3 will be 12. That's 12 unit pieces. So here we got this, which is going to be 12 plus 80 plus 30 plus 200. That would give you 322. Okay. All right, next is a lattice multiplication. We use lattice addition in section 3.2. This also applies to multiplication. And what this does, it has the advantage of delaying all additions until the single digit multiplications are complete. And this is sometimes referred to as a low stress algorithm. Okay. Now this is the procedure for using the lattice multiplication approach. You have to draw a lattice with a number of columns equal to the number of digits, and the first number being multiplied and the number of rows equal to the number of digits in the second number being multiplied. So for example, if we were multiplying a 3-digit number by a 2-digit number, this will be the setup for that. Three digits by 2 digits. We write the first number above the lattice with each digit over a different column and write the second number to the right of the lattice from top to bottom with each digit to the right of a different row. For each square in the lattice, we multiply the number above that column times the number to the right of that row. Write the units digit of the product in the bottom half of the square and the tens digit in the top half. If a product has no tens digit, we write a 0. And once each square is filled, you're going to add the numbers along each of the diagonals here of that lattice and write the sum outside the lattice at the end of each diagonal on the left or bottom of the lattice. So you start with the lower right and continue to work to the left. If the sum of the digits is more than 9, you're going to carry the tens digit to the next diagonal. After adding each diagonal, you're going to write the final product by writing the digits on the left and bottom of the lattice in order, starting with the top left and continuing the sequence to the bottom right. And the picture below that you see here represents how you're going to use the lattice multiplication to do 714 times 58, which is in this case gives you 41,412. But you know what? I'm going to do a couple of these examples, which is on the next page, using lattice multiplication. Now I'm going to start with 722 times 96. That's part A. Notice I have a 3-digit number multiplied by a 2-digit number. So this one we're going to do for the box. 722, I'm going to do 3 columns. 96 has 2 digits, I need 2 rows. The 7 and a 2 will be on top. The 96 will be on the far right, like this. And I'm going to have diagonals here, just like I did for the lattice approach for addition. Now, each digit on the top would be multiplied by each digit on the side, like 7 times 9, that's 63. So the 6 goes on top and the 3 goes on the bottom. Then I'm going to do 2 times 9, that would be 18. So the 1 goes on top, 8 goes on the bottom. 2 times 9, that's still 18. 1 goes on top, 8 goes on the bottom. And now I'm going to do 7, 2, and 2. Each digit will be multiplied by 6. So 7 times 6 would be 42. So the 4 goes on top and the 2 goes on the bottom. 2 times 6, that will be 12. The 1 goes on top and the 2 goes on the bottom. Then finally 2 times 6, that's still going to be 12. Notice the 1 goes on the top and the 2 goes on the bottom. And then next, I will add along each of these diagonals here. And I might need to do a little bit of regrouping if I have to. So here I have nothing to add to the 2, so I'll break that down. Here I got 8 plus 1, which is 9, plus 2, which is 11. I write down the 1, but I'm going to regroup by bringing the 1 over to the next diagonal and add those. The 1 that I carried over plus 1 will be 2, plus 8 will be 12, plus 1 will be 11, plus 2 will be 13. Write the 3 down, bring the 1 over on the next diagonal. So the 1 plus this 1 will be 2, plus 3, which is 5, plus 4, which will be 9. And I have nothing to add with the 6, so I'll bring that over. So here, 722 times 96. That's going to be these numbers right here that you see. That's going to be 69,312. That's what 722 times 96 will be. 69,312. So that's part A. Now part B. 369 times 69. Notice I have a 3-digit number multiplied by a 2-digit number. So I know I'm going to have 6 boxes set up like this. 3-digit number means I need 3 columns. By a 2-digit number, I need 2 rows like this. Because I'm going to put a 3 and a 6 and a 9 on top. Then the 69, the 6 and the 9 goes on the right side. And I'm going to draw my diagonals like this. Now I'm going to multiply each of these digits on top by the 6. So 3 times 6 will be 18. Now I only put 1 digit in those triangles. So the 1 goes here and the 8 goes there. 6 times 6, that would be 36. 9 times 6, 54. And now the 3, 6, and the 9 will each be multiplied by 9. So 3 times 9, that's 27. 6 times 9, 54. 9 times 9, 81. Now we're going to add along the diagonals here. So in this case here, I have nothing to add to this 1. So I bring that down. I add the 4, the 8, and the 4. 4 and 8 is 12 plus the 4 is 16. Write the 6 down, regroup by bringing the 1 over. 1 plus that 5 will be 6. Plus 6 is 12. Plus 5 is 17. Plus 7 is 24. Write the 4, regroup with the 2 on the next diagonal. 2 plus that 3 will be 5. 5 plus 8 is 13. 13 plus 2 is 15. Write the 5, regroup the 1 on the next diagonal. Well, 1 plus the 1 is 2. So 369 times 69 is this number, 25,461. 25,461. Or 369 times 69. Okay. That's how we use lattice multiplication to multiply 2 numbers. And pretty much it's easy, but the fact is you have to know what your multiplication facts are in order to do this. All right, now let's look at some mental math techniques with multiplication. One of them is front-end multiplying, like 78 times 4. If I do 70, since the 7 is in the tens place, 70 times 4, that's 280. And then 8 times 4 would be 32. And add 280 and 32 together, you'll get 312. That's how we use front-end multiplying. Another technique would be using compatible numbers, like 2 times 8 times 5 times 40 times 5. Let's group the 2 and the 5 together. That's a compatible number. Group the 40 and the 5 together. That's another set of compatible numbers. And then times 8. Well, 2 times 5, that's going to be 10. And 40 times 5, that's going to be 200. 10 times 200 times the 8 would be 16,000. And then number 3 is thinking of money. Like 84 times 25, you want to think of this as a product of 84 quarters. So 84 times 25, if you think of 84 quarters, that's $21. And $21 would, in cents, will be 2,100 cents. So 84 times 25 would be 2,100. So here's a homework example just like that. A car trip took 4 hours at an average of 59 miles per hour. Let's say I want to mentally compute the total number of miles traveled. So I'm going to write this as 59 times 4 and use that technique of front-end multiplying, which means this. The 5 is in the tens place. That would represent 50. Multiply that by 4, and that's easily going to be 200. And then take the 9, multiply it by 4. That would be 36. So here, 200 plus 36 would be 236. So the total number of miles traveled is 236 miles. Now let's move on to estimation with multiplication. Here we can use front-end estimation by taking 474 times 9, and we can start multiplying at the front. That 4 is in the hundreds place, that's 400 times 9, that would be 3,600. Then multiply the next digit, which is the 7, that's in the tens place, that's 70. 70 times 9, 630. And then we can add the two numbers together. 3,600 plus 630 would be approximately 4,230. So 474 times 9 would be approximately 4,230. And then the second method is the use of compatible numbers. Okay, compatible numbers are values that are easier to multiply together, like 524 times 8. That 5, of course, is in the hundreds place, so 500 times 8 would be 4,000. Now, a compatible number, let's look at this 24. 24 is 1 less than 5, so let's 1 less than 25. So let's use 25. Multiply 25 times 8, that would give you 200. And then add these together. 4,000 plus 200 would be 4,200. So let's try this homework example. A theater has 27 rows with 22 seats in each row. Estimate the number of seats in the theater. 27 rows of 22 seats in each row. And we want to estimate the number of seats in that theater. This one I'm going to do, I'm around 27 off, let's say to 30. Because 30 is closer to 27, or 27 is closer to 30. 22, let's round that off to 20, okay? And then I'm going to take that 30 and multiply it by 20. That would be 600, because 3 times 2, that's 6, and I got the 2 zeros behind it. So the number of seats in the theater is approximately 600. All right, so that does conclude this video on section 3.3, and that deals with multiplication of, 3.4, that deals with multiplication of whole numbers. That's section 3.4. Okay, feel free to email me if you have any questions about any of the problems that were discussed in this video and any of the problems that are in the homework from my math lab for this section.